All right, let's fill in these notes that I gave you today to kind of understand what a redox reaction is. Redox reactions stand for reduction oxidation reactions, and they come from these two parts of the word. So there's the read or red, and then there's the ox. Okay, reactions that involve the transfer of electrons, so let's write that in, transfer of electrons. And you can see that I put the E minus for electrons. And you have to know that both reduction and oxidation must happen at the same time. So we're going to use the word simultaneously. So both reduction and oxidation. So if somebody is losing electrons, somebody else has to be gaining them. Okay? What does reduction mean? Reduction means the gain of electrons. When I gain electrons, my oxidation number, if you remember what an oxidation number is, it's the number in the upper right-hand corner. That is going to go down, so a gain of electrons, by an atom or an ion. And oxidation number is going down. That's why we call it reduction. So it goes down and it reduces. The opposite of that, I thought I could move it all, I guess not. The opposite of that is oxidation, which is the loss of electrons. Let's get that pen back. The loss of electrons by an atom or an ion. And the oxidation number is going to go up. And we call that oxidation. Now we have a way of remembering this, okay? LEO, I might have said it in class when we were still together, means loss of electrons. And if it's a loss of electrons, I put the arrow pointing up on the L. That means that the oxidation number is going to go up. And GER, I'm going to put an arrow on the G going down. That means gain of electrons. And if you're gaining electrons, your oxidation number is going to go down. Okay? All right, oxidation reduction happened because of the desire for electrons in a chemical reaction to change, to move from one place to another. So some things, species, some atoms want to either lose or gain electrons. Oxidation reductions are mutual. That means they happen at the same time. Okay, I'm going to write the word simultaneous here. They happen at the same time, and one cannot happen without the other. So if I lose 2 electrons, somebody else needs to be gaining those 2 electrons at exactly the same time. Hold on, I got to figure out how to move this thing. All right, I did it. If one atom loses electrons, there must be another atom that is going to gain those electrons. So let's take a look at this example right here. And in the next lesson, we'll talk more about assigning oxidation numbers. But for the meantime, I'm going to put them in so that you can see them. So aluminum right here, let's see if I can get a pointer. That aluminum is a neutral atom. We did this in the beginning of the year. It has no charge. It's 0 charge. And if we do a reverse crisscross, we know copper is a +2 and chlorine is a -1. All right, we also know, because when we were together, we learned that this was a single replacement reaction. Single replacement. And because it's a single replacement reaction, if the aluminum is above the copper on table J, a reaction will take place. Remember that? Okay, so aluminum happens to be above copper. So aluminum is now going to hook up with chlorine, +3 -1, cross them down, and copper is going to be by itself. Now let's take a look and see what happened here. This aluminum went from a 0 charge right there to an aluminum with a +3. So I'm just going to write that down here so we can have it. Aluminum went from a 0 to an aluminum with a +3. Okay, what happened to those oxidation numbers? Well, it started out as 0 and it went to a +3. So it went up. Now let's go back. I can't scroll up very easily on this thing, but hold on, let me block you for a second. Aha, look what I did. I made it go smaller, so now we can see it. Hopefully you can see that. We see that the aluminum went from 0 to +3, it went up. And so because it went up, let's find over here, it says it went up, right? The oxidation number goes up. That aluminum must be oxidizing. So this aluminum is oxidizing. It oxidizes to the aluminum +3. Now let's look at the copper. So if we look at the copper went from a +2 right here. Okay, see that +2? And it went to a copper 0. And because it went from a +2 to a 0, its oxidation number was going down. And if we're going down, that arrow on the GER, it gained electrons. See, it went down. See the down up here? Okay, it was reduced. So this copper is being reduced. Oops, spell it right. Okay, so we have the thing that is being oxidized and the thing that is being reduced. All right, let's go to the next page. And simply let's fill this sucker in, right? It says one way that we can identify a redox reaction is to look at the oxidation numbers, right? We just saw that on the other page. So let's write that in. Oxidation numbers. I'm going to abbreviate numbers there. From the reactant to the product side. And every element that's involved in the reaction, the oxidation numbers used to track the movement of electrons. So we're looking at the electrons that are being lost, and we're looking at the electrons that are being gained from the reactant to the product side. Okay, oxidation numbers or oxidation states can be positive, they could be negative, or they can be 0. Okay, which is also neutral. We'll just write neutral in there, values. That can be assigned to atoms. We're going to identify how many electrons are being lost and gained by looking at these when they change, when they form their new bonds. All right, and don't worry if you don't understand all of that yet. You will in a little while as we go through this. Okay, always look in the upper right-hand corner, as that's where we're going to find these possible oxidation numbers. Okay, first trick number uno, okay, trick 1. All single replacement reactions are going to be redox. Replacement, you try to talk and write at the same time. Single replacement reactions, they're always redox. Always, always, always. Okay, so if we look at this zinc and hydrochloric acid, zinc is a 0, hydrochloric acid has a +1 and a -1. We would look at table J. Is zinc higher than hydrogen? Yes, it is. So it becomes zinc chloride and hydrogen gas. And we can go back and we could balance this too if we wanted to. Okay. So the zinc are by themselves on one side. Zinc is by itself on one side, but it's not by itself on the other side, and it's bonded on the other side. See how it's by itself here, and it's not by itself here? It's with the chlorine on the right side, so that chlorine and zinc are together, and zinc is by itself. The zinc is by itself on one side, and bonded on the opposite side. And if you look here, hydrogen is by itself on one side, right there, and not by itself on the other side. So if you have something that has, let me just write that in, that H2. These two guys are by themselves on one side, but they're bonded on the other side. Once you have something that's by itself on one side, but bonded on the other side, it is redox. Okay, that's like probably the best trick there is, because they're going to ask you, even though we're not taking regencies, they would ask you which one is a redox, and then that's what you're looking for. It's going to be by itself on one side, not by itself on the other. All right, and trick number 2 is if you see a double replacement reaction. Remember, double replacement reactions are compound plus compound, two compounds. Nothing is by itself, okay? And they switch partners. The Na is going to go with the Cl, and the H is going to go with the OH, which is water. It's just HOH is the same as water. Okay, if you have a double replacement reaction, let's write in the oxidation numbers. I'll use black. Hopefully you can see them. +1, -1, +1, -1, +1, -1, +1, -1. You see how none of the oxidation numbers change? Na was +1 on that side. Whoops, I went too far. And Na is also +1 on this side. It didn't change. OH is -1 on that side. It is -1 on this side. Didn't change. H is +1, it is +1. Chlorine is -1, it is -1. Nothing changes in a double replacement reaction, so it is not redox. All right, so those are the first 2 pages of notes. Go ahead, fill them in. Hit turn in on your Google Classroom so I can give you a nice easy grade. So we filled them all in, and I will see you tomorrow.